Hello, I'm Mr. Muskeluk, your AP Chemistry teacher at ChemAdvantage. Well, here we've got a problem on solutions and dilutions, and we're starting with an infamous material, potassium permanganate, a tongue twister, but it's a really beautiful substance. It's an ionic crystal. Here we've got potassium, so we know this is going to dissolve in water, as all sodium, potassium, nitrates, and ammoniums dissolve in water, and this is a potassium compound. The permanganate is a polyatomic ion that you should be acquainted with. Here is its Lewis dot structure without the electrons around the oxygen. And you can see we've got 4 domains. We all have a tetrahedral molecule, charge of -1. And this manganese with these 4 oxygens in it, this I should say permanganate, will grab electrons from other substances to change into a lower oxidation state. Right here it's at a +7. It'll go to a +4, even a +2 sometimes, but usually +4. So it grabs electrons from things. It's a inorganic compound, of course. And here it is, these purplish, blackish crystals, usually quite fine. And you can buy it as Condi's crystals. It's used in water filtration. It's also used in medication. If you soak a hand in it, as they were saying, for dermatitis, it ends up killing fungi. It's used as a disinfectant if it's diluted quite a bit in water. When it reacts, the final products are relatively safe. And here you can see it's part of the essential medicines. Right now, it's used primarily in veterinarian applications here in the US. Back to the problem where we take some of this and dissolve it in water. You can see we've made 2 solutions. Here's one with 0.0176 molar. This is the light pink one. Easy to make. Basically, you almost wave a jar of the potassium permanganate over the water, and a small crystal will get in there, and it'll make this light color. Very difficult to get it to this low of a concentration. And here's the more concentrated solution, darker in color. In fact, we could we could determine its concentration just by how dark it is. In this case, it's 0.166 molar, about 10 times more concentrated, and certainly 10 times darker in color. This stuff is great for staining things, and sometimes people will put this on wood to turn it into a nice dark brown. Every time I've worked with this, I've either stained my hands brown or my lab jacket brown. So when you work with this, wear some gloves and expect to get a little bit of brown on your skin eventually. But don't forget, it's used as a medication. If there was any fungi on your skin, they'd be dead. So let's get to the problem. Here we've got 2 solutions of this potassium permanganate, and the permanganates are reactive substance that makes this purple. We've got one where we have 35.7 mLs, okay, and it's concentration that I talked about. And then we've got another volume, which is a bit less than that, and it's a more concentrated solution. Calculate the concentration of the solution obtained when you mix these 2. Well, we're dealing with concentration. By now, you really should know this equation. This is something you just really should memorize. Concentration, molar concentration, not grams. We're talking about moles, the actual particles in there, times volume in liters will give you the moles, the amount that is actually in here. If you wanted to count how much potassium permanganate was in here, then you would figure out this concentration times volume. So we can figure out the concentrations of things. We'll do that in step 1, but let's go back to this equation. Concentration times volume in liters. Now I'll get my little line maker here, and when we do that, you'll know that the liters, because concentration is moles per liter. That's what this M stands for, moles per liter. And when you multiply it times liters, the liters cancels out, and you end up getting, of course, moles. And that's why this works. Concentration, this capital M that's italicized, is really moles per liter. Or if you did it, flipped it around, it'd be liters per mole, but then it'd be 1 over molar. So let's go to step 1. What is the total amount, and again, amount, we're dealing with moles, not grams, of solute in these two solutions? If you took these moles and multiplied by the molar mass of potassium permanganate, let's see, what is that? Let's go back to here. They'll give it to us. Here, its molar mass is, come on, it's got to be here somewhere. 158. Pretty large because we've got a metal and 4 oxygens. So let's go back to our problem. We'll find our amount of our first substance here because we'll be mixing the two. I'll pull out my calculator and I'll take my 0.0176, so low concentration, but you're not going to have a high concentration of potassium permanganate. It'll be like, oh, you couldn't see through it at all. And we're going to multiply times liters times. By now, you can know you can change these liters by moving the decimal point 3 places. The liters is the larger unit. This M stands for times 10 to the negative 3, but by now, this is fast. Move that decimal point over 3 places, 0, 3, 5, 7, and we have our answer. 6.28 rounded off. We don't need these extra numbers. There's only 3 significant digits here, times 10 to the negative 4. That is our answer. But that's a bit awkward. We're dealing with a low concentration, very small volume if you're dealing with liters. And here we get, if you had 6.28 times 10 to the negative 4, it's 0.000628 moles. That's a bit awkward. I advise when you're dealing with concentrations, and they give you milliliters and molarity, that stick with the milliliters. In fact, that's what I'm going to do next. I'm going to get my calculator out and do the same calculation, 0.0176 times 35.7. Now, this is milliliters that I'm calculating, and I get a nice answer, 0.62832. That's a lot easier to deal with and remember, and that's what I've done here. I've taken and multiplied by the milliliters, but you say, hey, that's wrong. Not really, because the liters still cancel. And I've got moles times milli. Guess what we'll get? 0.628 millimoles. A lot easier to write. And you know that milli stands for times 10 to the negative 3. That's the same number as this. Easier to write, easier to remember. And you don't have to do this, move the decimal point over. If you use milliliter and molar, you get millimoles. It makes sense. So what is the total amount of solute in both of these two solutions? The solute's the stuff you dump into the water, of course. So we'll get our calculator and do the same thing with our next problem. We'll just say, okay, I've already calculated the millimoles of the first dilute solution, this pink stuff, and I'm going to add to that, same method of calculation, 0.166. This is more concentrated molar, but it's a smaller volume, so we may not get all that much. 16.7. And this will give us millimoles. Added to these millimoles, it's more concentrated, but we've got less of it. So here's our total amount. It's 3.40 millimoles of potassium permanganate. If we wanted to find the weight, we'd multiply by that molar mass, that 150, whatever it was. So we know the amount. And that's the important thing. If you're using this stuff in a chemical reaction, you want to know how much chemical is really in there. So next, what's the total volume on mixing these two solutions? Now, it's possible when two solutions are mixed that you're not going to get exactly the same volume. If that's going to happen on an AP exam, they would tell you that the volumes are not additive. But with solutions like this, you're going to have the volumes add together. If you mix 35.7 mLs and add 16.7 mLs, your total volume is going to be the addition of these two. So let me go back to my calculator. Now I know I've got these moles, and I'm probably going to be using those later on. So I'm going to be clever here. I mean, I paid money for this calculator. I might as well use some of its functions. And one of those nice functions is you can store a number. Store it as, in this case, rather than doing an alpha, I'll just go X. That's easy to get back. So I'll save that amount of solute I've got in these two solutions when they mix, because that solute amount is going to be there. What's the total volume? I've got the amount. Now these two are mixed together. I slosh them together. My total volume is going to be, let's see, 35.7 mLs. It's nice being able to do this with mLs, plus 16.7. That's a lot easier than doing it with the liters. And this is my total volume. I've got a total volume of 54.2 milliliters. Now I've got the amount that's in this mixture when these two are dumped together. And I've got the volume that this amount is now in. And remember, our unit for concentration, molarity, is moles per liter. And here we've got moles, and here we've got liters. Oh, not really. We've got thousandths of a mole, thousandths of a liter, but hey, that's fine, because if we look at this, I'll get my line out again. This milli, times 10 to the negative 3 divided by 10 to the negative 3, it cancels. So we can take our millimoles and divide it by the milliliters. So this is both mixtures together. We're going to have this 3.4 millimoles, this 54.2 milliliters. Calculator. I've got my volume, but I also realize my moles. So I'm just going to say X, remember that was our 3.4, divided by our last answer. This calculator has the last answer. There's our new concentration, 0.0649 moles per liter, which is our molar concentration. Now, even though you use a calculator, see if things make sense. Here we originally had 0.0176. And here we originally had 0.166, so we mixed them together. But there wasn't all that much of this concentrated stuff, and there was quite a bit of this less concentrated. So our concentration has to be in between these. It's got to be between 0.02 and 0.2. Let's see, is this between 0.02 and 0.2? Yes, it's in between. It makes sense. It is an answer that makes sense. We followed our units. We did our concentrations. This is a great problem. You should know how to deal with concentrations and mixing solutions. Chemists mix solutions all the time. So chemists have got solutions, and you've done a solution of solutions. Okay, AP Chemistry, love it.